So, hello everyone. Okay, we got already an introduction, so I only add that I like to break stuff and I cannot solder, so I need someone to help me with this.
So, I was previously a lecturer, also working with Philip for the most part of the last 2.5 years as a security analyst. I'm very interested in why things break in specific ways, and I like puzzling them over those specific devices and seeing why they break, how we can fix them, how you can secure them. I can solder. I have a bit of a hardware background, although I haven't spent the last couple of years in hardware. I love playing bass guitar, and yep, that's me. You can get in touch on Twitter. So a bit of a storyline with regards to how we got to Mongoose OS and Xtensa exploitation. This all started with a badge that we received at a conference called Area 41. And Area 41 is a biannual Swiss conference held in Zurich. And there was a little device on there called the ESP8266. And this looked interesting to me because I also like to automate things and I like to optimize life. And I needed a small device with an e-ink display that would tell my girlfriend, hey, I'll be home at 7, I'll be home at 8. I mean, the analyst life requires a bit of time. If she then sends a message as a PhD, that also requires a fair amount of time. Whoever gets home first can see who needs to warm up the food or start prepping the food. Very simple use case that I wanted for this. And so I followed the ESP32, which is the follow-up device to the ESP8266. And yeah, as these things happen, I had a couple of them lying around on my desk. Didn't have time because I'm spending all of my time at work. And then Philip stole some that he actually hasn't given back yet.
Yeah, very nice. So another colleague of us built a small device. It's called Biotech, and it's basically a humidity sensor for the plants in our office because we tend to not water them. And so, but we actually built some vulnerabilities into this to train a bit more how to work with IoT devices. And suddenly a real-world customer popped up and claimed, yeah, we have a project based on ESP8266 and Mongoose OS, which is funny, because we talked a bit about this and I've asked them, did you do any protection against buffer overflows? And they're like, no, we don't need this because our program runs bare metal. We don't have an operating system. They use an operating system, but they don't have one. So yeah, we wanted to prove them wrong.
So I'll talk you through some of the focus of this talk. First, we're going to talk a bit about JavaScript and the problems introduced by using JavaScript on IoT devices. Then we'll talk about mitigations that are not in place on most IoT devices. We're going to talk about the operating system and the layering of multiple operating systems, actually. And then we're going to talk about the pen testing approach. How do you attack this device? How do you approach exploring all of the attack surfaces?
And then we jump into the IoT cyber kill chain by exploitation. I had to add this, so sorry. We started to make a paper, so we talk a bit about our paper, and then we show some exploitation, which is basically simple demonstration of that buffer overflow exploits are actually possible on this architecture because it differs a lot from other architectures. And then we show that rope chains are theoretically possible on this platform. And we talk a bit about persistence. The CNC part is for later presentations.
And then we finally conclude with what you actually get for $2 security and other approaches for securing your projects. So, security and privacy are silent prerequisites. However, not too many stakeholders will talk about them, but everybody seems to take them for granted.
The problem is securing a solution usually takes a long time and much time, And this is a strong contradiction to the market requirements. This is not animated.
And we have a non-animated GIF. What you see on screen is the abstraction that is currently happening when you deploy Mongoose OS on these IoT devices. So if this was actually running, you would see a 3-step process. Basically, you select the interface to your device, you select the Wi-Fi network, and then you can start coding. And you start coding in JavaScript. Now, all of the hardware guys amongst you would be thinking, why is he talking about JavaScript when we're talking about embedded devices? And this is the same kind of reaction that we had initially. So you can go to the Mongoose OS website and you can get set up and deploy your code in basically something like 3 minutes. And this makes the initial learning curve for developers very low, but it brings with it some other problems, or it introduces other problems. And as you can see on the Mongoose OS apps list, we have a whole bunch of JavaScript examples. I don't see any C code there. I don't see any other embedded languages that's listed. So just JavaScript, JavaScript, JavaScript all the way. So if you have a look at these stats, the graph on the left shows the JavaScript developer average salary in US dollars and the C developer salary. So the C developers are a bit more expensive. And I mean, you might make a business use case for hiring people that are not as expensive. Anyway. And JavaScript, we also contend that with a lot of these single-page applications that you have available online, a lot of people are focusing on web development technologies, but might also be interested in IoT.
So you have web developers doing hardware development, which is interesting. And on top of this, there is basically no security implemented on this architecture, or if we talk about embedded operating systems, basically they do not have much protection, like ASLR, ESP, or stack canaries. Usually this is because we have very limited resources on those devices and they run on low power, so we cannot add a lot of more cycles to check for security, but we're lucky with the ESP part because ESP is not the espresso device, and this is a no executable stack, and this is already the case on the Xtensa platform. So we have a no executable stack, but everything else, no one implemented it, and we will see how this goes out in the future.
So to give you a bit of background on the ESP devices, if you don't follow this specific chip, this was not well known in the West until I think it brought out a dev board for this in 2014. They also proceeded to translate most of the documentation. I mean, time documentation, pick one. So they translated the documentation and made the documentation available, and then it became more popular in the West. So the device is very cheap, it's sub $1, and the dev boards typically go for anything from $4 to $8, depending on what you get. So the embedded underdog with the language availability became more popular. Today, what we see with Xtensa, the company providing Mongoose OS, they have a lot of big customers. What's interesting to note here is that Mongoose does not only deploy to Xtensa, ESP32 and ESP8266, but also to other devices, for instance the STM. And there seems to be a lot of interest from big vendors in deploying simple Wi-Fi connected devices.
Also, if you look at the architecture itself, the Xtensa platform is basically used in a lot of products you have in your everyday use. or not everyday use. It's actually used for the motion tracking in the Microsoft HoloLens. It's used as a DSP coprocessor for the AMD graphics cards for sound processing, and it's actually built in a lot of DVD and Blu-ray players, or AVRs if you have some of those. And additionally to that, because it's on AMD graphic cards, it's basically in every PS4. So you have around 60 million systems alone for this. But those do not run Mongoose OS.
So essentially what you get with this Mongoose OS and with this $1 device, you get a fair amount of actual hardware in this device. And then naturally you get cloud integration, so easy integration with AWS, Google Cloud, Microsoft Azure. And naturally if you want to communicate with those services, you need some lightweight IP stack for communication.
Additionally, you have a dual-core CPU on the most LX6 versions of the ESP, or better, of the Xtensa processor. In most setups, one core handles the communication, and the other core handles some kind of operating system or metal programs. Additionally, you have also for connectivity, Bluetooth and Wi-Fi, and you have GPIO for adding other components like temperature sensors, name it, IoT stuff.
So getting back to the abstraction caveat that I covered earlier, what is really the problem with allowing JavaScript developers to develop for your environment? What we're doing is we're trading infrastructure awareness for a decrease in learning curve. And this, from our perspective, is a bit of a problem.
So basically, as our customer claimed, nobody knows there's an operating system.
And nobody knows how memory management is working or handled.
And you just add some weird library to have network connectivity and you're done.
So our recommendation or our concern is that if you're going to provide black boxes for people to develop on with very easy integration and API access, etc., then you need to go ahead and you need to provide safe defaults for people to work with. So ASLR might be a concern. If you do code signing in the device on the operating system, you need to do this correctly, but we'll get to this later. And overflow handlers need to be implemented. So essentially, instead of having a bare metal device, what we actually have running on the device is, well, turtles all the way down.
So we start with the XTOS, which is basically inside of the processor. You cannot change it after it has been shipped or produced. This handles some basic hardware abstraction layers. You can implement drivers for your peripheral systems there, and the trainings for those are quite expensive, so there's not much information about this operating system. Additionally, on top of this, at least Espressif recommends to use FreeRTOS or RTOS, a real-time operating system, which is mostly used for multi-threading and handling your communication data and some multitasking in your application. And on top of this, you have Mongoose operating system or Mongoose OS, which is basically 80% web server, 70% JavaScript engine. And it adds a lot of libraries you can just use and you can start quickly. So this is more or less a framework, not really an operating system.
So, getting back to attack surfaces, if you get this device, how can you approach securing it? So, how do we secure most things? Well, we're pen testers, come from a security environment, we like to break things, like we said. So, we need to know what you have a look at. And from this barely readable slide, you can see that there is quite a bit of attack vectors that you can go ahead and have a look at. And I'm going to summarize them for you basically and just say that the most important things would be data at rest. So with data at rest, we need to know where do we store the data, how is the file system structured, are things encrypted at rest, how is access controlled to that, what parts of the operating system can handle this in user land. Then we have data in motion. So what has changed in memory? At what point are things available in memory? At what point do we send information over the network? Again, it's interesting to know in what format. And then how are things affected during processing? So we need to know about data at rest, we need to be aware of data in motion, and we have to go ahead and look at all of the interfaces that interacts with the device, or even how user input is handled, but we'll get back to this a bit later.
There is more. So on top of this, you should consider information leakage, because if you by default build C code for Mongoose OS, you basically use 3 commands to compile, flash, and run the program. And if you compile the code, it is basically uploaded to the cloud. It's compiled in the cloud, so your source code goes to a third party. And then you download the binary which you cannot verify and flash it on your device. So basically, if you're a super secret startup, you push your code to the cloud. It is possible to do it locally, but our customer, for example, they uploaded all their code into the cloud, including internal passwords, and it was quite fun.
And then something we recently learned at hardware.io, you can go beyond the software level of control and you can play around with hardware glitching or voltage glitching. And with this then you could most likely also do some interesting things like control the PC. But we won't, or we don't go into that. So a bit of background, we started this shortly after the Mirai botnet information was released, and what was interesting to us was the fact that the Mirai botnet, essentially you could remove the exploit, or you could remove the problem by simply resetting the device. And we don't really like that you have to reinfect the devices, regardless of how you get on the device, if it's your default passwords or not. So things we did and things that we have POC of is we first exploit the device, then we go ahead and get remote code execution because, well, we like running our code on devices that we don't pay for. And we would also like persistence because persistence, it was the one thing that Mirai basically did not have. And we would like to have our code still run after the device is reset. Coming from Africa, we had a lot of brownouts and power outs, so you need persistence and you need to run this. And then command and control, we haven't yet finished. The document there says draft, so hopefully next year we can release a full document on this. This took a lot more time than we expected it would take.
So the first thing we needed to prove is actual buffer overflow exploitation possible on this platform, because it has a bit of different stack management, and so we initially wrote a small sample code. Basically, this is not the real sample code because the return address override is missing, but anyway, so we create a crash, we overwrite local registers A2 to A8, and additionally we overwrite A0 to A1. A0 on Xtensa is basically more or less the program counter, so your next instruction goes there, and if you execute this, the buffer will be overwritten, and we have our new address in A0, and we have control over the execution flow. When you go to the next slide, we have a demo for this, but we thought we could do it here in the front, which we actually cannot do. So you could later go to this link. Basically what happens here is the system booted up. I have the debugger connected, and it connects to the Wi-Fi, which is the middle finger you see in the console. And after it booted up, it prints exploit test, exploit test, exploit test. This is happening because if you overwrite a PC, register shift windowing is happening. So what happens is it's now an endless flow because we just overwrote the EIP, if you want to say so. So every time it returns from this function, it returns to the old return address, which is basically the same function. So we have control over the execution flow, but we cannot really do something because the stack is not executable.
But we somehow still managed to discover something, and we did a responsible disclosure with the Xtensa team. They were also very helpful and communicative and responded and allowed us to publish within 1 week after they let their customers patch.
And I also committed my typo, but anyway. So basically, we found a crash while handling HTTP multi-path requests. Essentially, if you give the wrong length for a multi-path request, it tries to read more than it's actually there. So the code is handling this properly. So they trigger an exception, but the exception handler is just doing nothing and continues the execution. And after this, the program tries to read from memory which is not initialized, which gives us basically a crash, as you mentioned forward.
And we have a crash.
Yeah.
So what we proceeded to do, we started something called Hack Nights, and we would just inspect the actual code. And like a good pen tester, usually we try to also provide a solution to the problem. So we spent a lot of time over patching this, especially Philip. So some of the functionality of the web server in Mongoose actually disappeared. So this took some debugging to try and understand, to find the issue in about 7,000 lines of Mongoose OS code. The Mongoose OS, by the way, is largely based on the Mongoose web server. So we'll get into that a bit later. So this is typically our approach to attack a system, to try and break it, and then to see what caused those actual problems. So we can see how debugging breaks it, and how can we go ahead and make the device actually more secure.
Okay, so shortly after we released the advisory for this, it's just a DOS for IoT. This is already a lot because crashing some control systems is always fun. But anyway, so the CTO of the Mongoose or Xtensa did a small blog post about this, and basically he says that you should not run the device in server mode, and you more use it like a client which talks to backend, reports data, waits for comments, which already sounds a bit like a botnet, but it is not. And he says you prevent a lot of security attacks if you don't run it in server mode, which is kind of a bold statement because, as I already said, around 80% of the Mongoose OS code base are web servers, so it's interesting. And he recommends to use the MQTT client libraries if you look.
So, a colleague of ours adapted a fuzzer, and after about 30 seconds of fuzzing on some of the code, found that there are also problems in the client-side communications. So Xtensa recommends not using this as a web server, rather as a client, but then client code is also interestingly problematic.
Actually, what we have here is a remote code execution in an unencrypted protocol. So as said, as soon as you have control over the network where the device is running in, you basically can have a remote code execution directly, not only crashing. So this was also, it was just 30 seconds of fuzzing. So if you go longer, maybe you find more interesting stuff.
Yeah. Our colleague didn't actually go ahead and submit the patch code because he didn't care much.
Okay.
So, yeah.
No. Okay. So now we go to blockchains. You may ask why, and this is because of NX. The stack is not executable, which is kind of sad because back in the days you just popped your shellcode on the stack, jump there, and you're good to go. So what are blockchains? Basically, we're reusing instructions to alter the execution flow. And these instructions we take from the executable part, from the ROM. So we have executable code lying there.
Yeah, so if you think about it, for the Rick and Morty fans of you out there, blockchains are basically pickled Rick. And with this I mean, we build mutations, or we build useful things from existing code or existing pieces in order to be able to accomplish more interesting things. So we want to reuse the compiled assembly code to do more interesting stuff.
So, how to build Franken code?
Yeah, so this took me a while to understand. Essentially, with gadgets, what we need is we need pre-existing assembly code that has been created and deployed on the system. And this means that if a given flow of gadgets exists or pre-existing code exists on the system, that we can go ahead and reuse to basically put interesting things in the registers, then we have a perfect gadget.
Yeah, but however, due to the lack of proper register usage or different handling of the stack due to the register windowing on the Xtensa platform, there are not really perfect gadgets like those we have there. So the compiler does not create those. So we have those fake gadgets here. We just build some code which actually does what we want to do. Maybe in a bigger code base you find those. But this is just to prove that you actually can do a rogue chain. So basically we have one gadget which is basically populating the shellcode onto registers, and with the next instruction, write memory, we put this to executable memory. After this we just need to flush it, this is the isync instruction, and then we can jump to the code we just wrote on the executable stack basically, or executable part of the code. We're currently searching for some ways to have more complex gadgets. So you could do, we have a proof of concept for chaining at least 5 instructions, but this is not enough to have a reliable exploit. So right now we use this to demonstrate, but we're currently working on finding more complex gadgets to build actually some real-world code. So we have achieved the code execution, but this is only if you see, and we now want to have persistence. So if you look at Mirai, this is only in RAM. So if we unplug the device, replug it, basically it's better than having a virus scanner. It's just a way. You just need to change the default password. Additionally, we could just flash a new firmware. This, however, removes the original functionality. So if your fridge is not telling you to buy milk anymore, you will probably notice that something is going wrong. So just reflashing it will not work.
Yeah, and since we want persistency on the device, but we don't just want persistency, we want persistency plus the original functionality, we need to be able to add our code and have it survive the actual boot cycle. So we do this by patching the out binary and by redirecting to the hard-coded entry point.
So, but yeah, we are running on the device itself, and it's a so-called ROM, so we can only read on this memory. But that's actually not true. We searched for the firmware updating code, and in this code you have a reference to something called SPI flash enabled write. So after you executed this method, you can enable writing to the ROM, and then flash your patch and reboot, and you have view functionality plus original functionality. So we tried this, and yeah, not so much. The bootloader told me checks are incorrect. So I had to dig deeper in the code and go to the bootloader code, and I discovered that they have two kinds of hashes or checksums, which is basically a char checksum. If you don't enable secure boot, this would be checked, but if you just null it in the firmware image, it will not be checked. So there is no char checksum, there's nothing to check, all good. But there's additionally an XOR checksum, which is basically a hard-coded value, and you go through over all the image, and you can do this with 5 lines of C. So you go over your patched image and recalculate this, and this checksum is the same on all espressive devices, starting from the ESP8266 to the ESP32 and all the newer ones they have. It's a static value.
So what is recommended as the secure IoT solution if we're talking about very low priced devices? The Xtensa blog mentions Mongoose OS that you use with the ESP devices, you add a cryptic chip on this, and you communicate with the cloud. So this is $2 security. So what do you get for $2 security? Well, you get a device that basically dies on deployment.
Like an ATM. So you deploy deprecated technology, and for us as pen testers, we see IoT devices basically like unprotected mobile devices, like your smartphone 6 years ago. No one right now has implemented any modern protection mechanisms. There is some work of Jos Wetzels, who did implement some boot-time ASLR, which is kind of interesting. And but if you look at it, the environments are quite the same. So we can just go back 10 years, and all the lessons learned in the mobile environment, we can adapt to this.
So taking a step back and looking at the broader view, how can you then go ahead and secure your project?
Just by outsiders. This is the only way you can get out of the box thinking.
So naturally we'll recommend using external testing teams because we work for a company that's not inside yours. But the point there is to basically get people to have a look at it from a zero knowledge perspective. So it could be an internal team that doesn't have any information about the project.
As for a customer, for example, their hardware developer told them this is a bare metal OS, this is a bare metal application basically. We don't have operating systems on here, and they needed an external advisor to tell them there's much more. And for this, which is often forgotten in management processes, is that you need to ensure that your library dependencies are basically updated whenever a fix is released. For example, if the web server is attackable, and there are no excuses for not having an update mechanism. Luckily, if you use Mongoose OS, this is already covered, at least if you compile in the cloud, because in the cloud you get always the newest code, so you're in the latest branch. And they also have a really nice firmware update mechanism, but yeah, it works with SHA-1, so.
So, future work that we would like to have a look at, we still need to look at the CNC. Our colleague already showed that you can also do some interesting work with more intelligent fuzzing.
Yeah, also right now the persistence code is about 10 lines of C code, which I need to translate to shell code. This is one of the next steps I will do.
And then standard protections could be implemented on this platform. Luckily, most of these mitigation techniques already exist in the real world. I would suggest you follow up on the work of Jos Wetzels. He's done some very interesting talks on securing IoT devices with these real-time OSs. And he basically said that if you can implement the code and deploy the code and it doesn't add more than 5% to the code base, then it doesn't really affect the energy consumption on the devices that much. And then our thanks. Thank you guys for joining us. Some of you a bit late.
Yeah, Area 41 for the badges, because this sparked our interest into working with IoT and embedded devices.
Xtensa for Mongoose OS. This has given us much fun playtime over weekends, and we were happy to contribute spelling mistakes to their code base.
And then to Joe Sandin and Neil Corbin, who actually did a lot of documentation and reference work. So look those guys up, they have done some awesome stuff, especially Neil Corbin wrote an awesome book about the ESP universe, so this is really good.
So both of us should actually be in Zurich. I should be doing INFOSEC work, and Philip should be testing.
Destroying stuff.
Yeah, so thanks to our companies for allowing us the time to come and do this.
Yeah, basically my boss man for giving me preparation time and a bit of research time.
And then finally to anyone that drew pictures that we blatantly stole, and hopefully nobody will claim copyright. So how to get started for the students among you who are interested in very small devices that want to get started for $5 or $10. You can buy an ESP32 dev kit. You can go to AliExpress if you trust them. You can go to some European sites that sell the same devices and dev boards. If you want on-device debugging, then you need something like a Shikra to interact with OpenOCD. Naturally, you need to buy all the cables, you need to wait for the device, and then you can install ESP-IDF, download and flash the code. Again, the previous slide had a reference to some interesting introductory material if you want to get started. We would also recommend that you don't go the JavaScript route if you don't have to.
Play with some C.
Yeah.
Exactly.
So a picture from Switzerland, somebody chewing a Toblerone and putting it down.